This lecture is about how we train these neural networks, and the agenda will be first we will just go over the basics, which will be required actually to talk about the whole process. And the basics I think we have already covered. It's just a recap. Then we will talk about optimization, and this is like the main step, which is the training process. And then we'll briefly talk about backpropagation, which is again a step which is used while training these networks. And then we'll try to cover some of the practical aspects when you do programming assignments. I think it will be very useful. And finally, I will show you like some CNN variants and like some motivations why those CNNs were designed to wrap up this lecture. All right, so let's begin with the first segment. Now, let's first try to understand the concept of network parameters. We have been talking about this a lot, but let's make sure that everyone understands this pretty clearly. So in a neural network or in a convolutional neural network, you will have input. Okay, so there is a distinction between data and parameters. Both are actually storing some values, some numbers. Okay, so in that sense, they are like similar things. But data is something which depends upon your input sample. Okay, so what value like you will have in this activation will be highly dependent upon what image you have used as your input. If let's say this is like activation map in some of the after some of the intermediate layers. Okay, so that's one thing. Then there is one more thing which is called parameter or these kernels, which will also control what these values will be, right? But these values will not change by changing your input sample. Okay, so if you have a kernel which has certain values, for example, this 3x3x3 filter, it will have 27 different values. Those values are actually representing your network. They don't represent your data or your input images. Okay, so they are part of your network. And these are called parameters, and these will be learned when we train the network. Okay, so for convolutional neural networks, these kernels will be learned. For example, in this case, these 27 different values. So how it works is we initialize the weights randomly, which means when you start your training, you will randomly select like some values for these kernels. And as you train your model, these values will be changed. Okay, so these are the parameters. And in neural network or fully connected layers, your neurons will contain like the values or the activations. But when you're trying to connect two different neurons, you will need some weights to compute those linear combinations, right? So those weights are the parameters. And again, those weights at the beginning, you will initialize randomly. But as you train your model, those weights will be changed. Okay, so these volumes are, again, as I said, they depend on the input data and also on the kernels, but these are not part of your network. This is just data flowing into your network. Now, if you look at this example here, this is the input image and the kernel which we are striding, right? The red kernel or the green kernel, that's the filter. So those are the parameters. Those are the weights which will be learned. So we'll try to learn this filter. And again, this we just saw in the previous lecture. These are not weights. All these are just activations. And this is kind of a data flowing into your network. And this will vary with the input image you have. But how you obtain these activation maps using these convolution operations, those are the network parameters which we are going to learn. Okay, so a general CNN architecture, as you all know by now, you have input image, you have certain convolution layers, some subsampling layers, or some normalization layers, and your data will flow in your network. You go from feature maps to feature maps, and finally the output. And the way it works is you have your input image, and as I said, you initialize these kernels randomly. So even without training your network, you can actually have an input image, and you can still get these activation maps, and you can get some kind of prediction. But since the network was randomly initialized, it was not trained, what will happen is you will get some kind of output which will not mean anything. I mean, it will not be the right prediction, right? So then the whole idea about training is you take that prediction, whatever that is, we don't care about that, and then try to compare that with the actual ground truth, okay, the value which the network should have predicted. And then we try to say, okay, this seems like a bad prediction, or this seems like a pretty close, but it needs to be improved, right? So we can kind of estimate like how good the network's prediction is. And what we do is we design like a loss function, which tells you how good your network's prediction is. And then based on that estimation, it will just give you one value, how good your network is. And that value will be used to update all the network weights. So there's like a backpropagation here, which goes backwards. And there is a feed forward operation, which happens when you start with the image, apply the convolution, get this feature map. So that's called like the feed forward, going forward, getting the prediction. Okay, so there are two operations when you train your model. We'll talk about that in more detail later. So the basic training operation, I think, again, we have covered this in the past. You have your training data. So you don't train just on single image. You train on lot of images. And that's one of the limitation of deep learning. You require a lot of data. Okay? So you have all these images and you can extract features, or you can use like CNN to extract features. And then you need these labels, which are called ground truths, right? So then again, for all these samples, you try to make predictions, and then you make use of these labels to say how good the network is doing. If it's doing bad, you will penalize the network. You will say, okay, the weights are not good, improve the weights. So that act, when you say that improve the weights, that is called network training. Okay? So during training, all you're doing is you're trying to change the weights of those kernels. That is called network training. So again, so I think all of those are basics which we have already covered in the past, but still, if you have any questions, please ask now, because we need to understand like all of those basic terms before we move on to the next step. All right, good. So it seems like no questions. So that's good. Let's quickly move forward. And I think this will be the last segment, and then we will stop there. The next segment is the optimization process. And this is like the core of network training. And I think the important part you need to understand is the concept of loss function. As I said earlier, loss function is something which tells you how good your network or how bad your network is performing. Okay, so it is a way to tell how good the network is doing or how bad the network is doing in terms of the prediction, which again, it will, if you think about this, it will vary a lot from problem to problem. Right? So right now, we'll just focus on, let's say, classification, where we just say that, okay, this class is present or this class is not present. So it's just one number there, right? But if you think about this, that's classification. If you go to detection, the prediction will completely change. You will have that number which will say, okay, object is present or not, but then you also need to predict like the location or the bounding box. And it will get more complicated as you move to, let's say, segmentation, where for every pixel, you will have to say which object category is present. All right. So it depends on like what task you are solving. But right now we'll focus on just classification, where you just say that whether object is present or not. And again, that concept can be easily generalized to other tasks as well. Okay, so this network training is actually a kind of optimization. And what you're optimizing is you're trying to optimize the network weights so that whatever prediction your network makes, it's actually very close to the ground truth. And the idea is, let's say your loss function is defined by this formula. This big W over here, these are like all the network weights. All right. So not just one layer, one kernel. This comprises of all the weights you have in your network, which means if you have 3 different convolution layers, or in case of LXNet, you have like 6 different convolution layers. So all the weights there, like all the kernels in first layer, second layer, third layer, so on and so forth. Right? So this W represents all those weights. Then these weights will be input to your loss function. And what's happening here is you will need a ground truth. Right? So this loop is going over like all the samples you have present in your training data. And as we have discussed earlier, like In your training data, you will have a lot of samples. Let's say you have 10,000 samples. Okay, so n will be 10,000, and you will go to each image, and then you will compute loss for that image, right? So in this case, L is your loss function, then F is your network. And you know that the network takes an image as input. In this case, xi is the image, that's the input, right? And again, these are network parameters. And these parameters are like, let's say, the current state of the network. If this is the first step, then these will be randomly initialized. Okay, so given a network, all those hyperparameters which we discussed, which define the architecture of the network, you will send one image as input, you will use the weights, and that will give you the prediction. Okay, so for example, let's say it's a 1,000-weight classifier, then the network will predict 1,000 different values, and then you will pick like the most activated value, or whichever class is like being predicted at this time, right? So whichever has the highest value, you will say that, okay, this is the network's prediction. And then what you will do is you will have the ground truth. For this image, you will know that, okay, which object was present, right? So input to your loss function is the output of the network and the ground truth. And that's why we need ground truth to train your network. Then you will make some kind of comparisons. We'll talk about that, like what kind of comparisons we can make. But you can easily say that, okay, whether this prediction is good enough for this kind of ground truth, right? Whether it's close or it's a very bad prediction. So this function will give you some value, right? And let's say that's ranged from 0 to 1. So 1 means very bad prediction, 0 means very good prediction. It means you were able to predict the ground truth. So then you will average that over all the samples, all the training samples. So then essentially what's happening here is this loss function is telling you like the average loss, like how good your network is performing on this training data. If this value is 0, then you can say, okay, the network is actually very good. It didn't make any error. If the value is 1, then you say, okay, it's pretty bad. It's useless. Every time it's making a mistake. Okay, so this loss function is giving you a sense. It's just giving you one number, which determines how good your network is performing at that stage. And remember, all of this also depends on these weights. So now what we want to do is, whatever loss we got, we try to minimize that loss. So we want that loss to be 0. And to do that, we will try to modify these weights. So we want such a weights which will make this loss value equal to 0. So this is the optimization process which we'll have to perform. So let's try to understand like how this optimization is done. So we use gradient descent, and you might have studied this algorithm in the past in some of the courses, maybe in statistics or so. But I will give you like a quick recap of how this gradient descent works. So, and again, I mean, there are a lot of other optimization algorithms you might have, maybe in numerical calculus, or you might have studied. But gradient descent is one of those which I think is very useful in network training. And it's a way to minimize the cost function. In our case, this is the cost function which you want to minimize. And these are the parameters which you can change to minimize this loss value. All right, so let's try to understand how this gradient descent works. And again, we'll just go with like a very simple example, a one-dimensional, one variable. But again, that can be easily generalized to high-dimensional space. So let's assume we have a function f which operates on value x. All right. In this case, let's say x is like just one value, which can be represented by this x-axis. And y-axis is the response of that function. Right? So for each value of x, you will get some kind of response. Okay, so if you think about this, f in this case is the network, and x is like the parameters you have. Okay, so when we try to optimize this, when we try to optimize like this function, then we want like the minimum value of this function f. Okay. Oh, sorry. So f not the network. It's the loss function which you're trying to optimize, right? Sorry about that. So this is the loss function f, and we want to minimize the value of the loss. In this case, we can see that the minimum value is at this location, right? The bell location, and it can't go like any further down. That's the minimum we can achieve. So the optimization, what it will do is it will tell you, okay, for x at this position, you will get the minimum value. So when we perform the optimization, we are trying to estimate the value of x. So if you map this analogy, if you map this with like the network training, and f is a loss function and x is like your weights, in that case you will have similar kind of curve, right? For different parameters you will get different values. It will be a function, and what we want is we want to find the parameters of the network. So we want such a parameters where the value is minimum. Okay, so how we can do that? So as I said, we randomly initialize the network weights. In this case, let's say x is our weights. We randomly initialize, let's say we get at A1. All right. And that will give you a loss value of something like at this point. Now we know that this is the loss. By looking at this curve, I can say that I want to go towards this direction. Right. Then I will be able to move this parameter towards the right. So what we do is we just find derivative at this location. And you know that derivative just gives you the slope of the curve. So if you compute the derivative, it will be something like this. And in this case, you can see that the slope is actually in the opposite direction, right? So it will have a negative value. Okay, so you can see here that it's 1D function, we can call it a derivative. But if it's like multinomial function, we'll have to compute like a Jacobian, or we can say like higher order derivative, right? So we'll have to compute partial order derivative for like different dimensions. But don't worry about that right now. Let's just assume that it's a one-dimensional function. We can find the derivative, which represents a slope. In high dimensional as well, it's like kind of slope of the curve. So if we have the slope, then we know like the direction, right? It's negative. Then what we can do is we can actually follow the direction of the slope. Okay. So if we follow that, then we can move like one step ahead. So this is like the increment we want to take. Now look carefully. First of all, this is again like some kind of hyperparameter, so don't worry about this. So we want to go from A1 to A2. A1 is the original location, and we compute the derivative of the function, right? And this gamma over here, it's again a parameter, and it's called learning rate. And learning rate, again, it's a hyperparameter. When you train your network, you will work on that a lot. So let's try to understand what that learning rate is. So that learning rate is just like how big your steps should be. Okay, so if you focus on this part, which is like a derivative of this function, so as I said, this is going to be a negative value because the slope is negative, right? So if it's negative, there is a minus sign over here, which makes it positive. And gamma is like a parameter, it will always be positive. Then what you're doing is you're actually adding this amount of value to A1, right? Because negative will cancel negative. So if you add something to A1, in which direction you will go? You will go in the right direction, right? Towards right, because you're adding something to A1. And how much you're adding? That is controlled by two things: the gradient, what is the slope over here, and the second is this gamma parameter, the learning rate. So these two control like how fast you move towards the right, or how big your step will be. Okay, so if you can compute the derivative, you can actually move in this direction. And once you are at A2, you can again repeat the process. Compute the derivative, and again, it's like a negative slope, but this time like the value of the slope is actually reducing, right? Because earlier it was like more slant, then it's going down. So then again, you're using the same learning rate, you will move to A3, and you can keep doing that. And what will happen, you can see like as you're going close to this point, your slope is actually getting lower and lower, or the derivative is going like lower and lower. And at this point, when you try to compute the derivative, it's completely going to be a horizontal line, which means the derivative is 0. So if your derivative is 0, then the second term is going to be 0, which means your value will not change. Therefore, when you reach a point when your value is actually not changing, it means you are kind of in the target location. In this case, it's the minima here, and that's what we want. So we wanted to find this value, right, a star, and that's how gradient descent help you like find this value. And again, this is one dimensional, but you can easily generalize this to high dimensional space as well. So that's exactly how your network training works when you try to use a gradient descent. But things are not that simple. Okay, so I will cover like some of those aspects why it's not simple. But as I said, like gradient descent, it's used for like optimization of functions. Now, if it's a convex function, okay, convex function is something which will have only one minima. Okay, so this is a convex function. Then you can use gradient descent and you will definitely find that minima. But your loss function will never be a convex function, right? It's going to be a very complicated function. It's always be non-convex, something like this, which means that you won't have like just one minima, you will have a lot of minimas. And then the goal is when you optimize your network, you're just trying to find local minima. Okay, if you are in this neighborhood, you are interested in this. If you are in this neighborhood, you are interested in this. And again, there could be like a lot of other local minimas. And that's one of the issues like when you train your network. And that's the reason when you train your network at multiple times, you will get different results. The reason is you are initializing your weights randomly, right? So it could be like when you initialize your weights, you start from this location. In that case, you will end up at this location. But another time you might be initializing with this point. In that case, you might end up at this location. Okay, so this will give you like two different networks when you try to optimize it. All right, so all that is good. I think I already covered all these points. Now let's see how you train your CNNs with this simple gradient descent algorithm. So you have n training examples, right? Xi is your image, Y is the label, and let's say Fx is your feed-forward network, which takes image as input, and it will make some kind of prediction, which should resemble this label. And then you need some kind of loss function, which will again take like the parameters of the network, theta over here, and it will take the image and also the label. All right. So with all this, all these set of information, what this loss function will do, it will tell you how good your network is doing, right? As we discussed earlier, it will just give you one number, and you will use that one number to actually update your weights, and the way you will update the weights is based on gradient descent. Okay, so that one number is actually nothing but some position in this curve, right? And based on that number, if you compute the derivative, you can actually move towards the minima, and you can update the values of your weights. All right, so this x-axis is like your model parameters, and this is the loss function of your CNN. And at any time, like if you have certain set of weights with any input, if you try to predict the loss function or the loss value using the loss function, you will be like at any of the locations in this curve, and all you want is you want to move that point to the local minima. Okay, so let's quickly go over like some of the loss functions which can be used to estimate how good your network is doing. And the most popular one is cross entropy, and I think you will use this a lot. And I will also try to briefly explain like why it actually works. So the simple equation for cross entropy is, so you have the hat is the predicted value, and the value without a hat, that's the ground truth. Okay, so let's treat this value as 0 or 1. 0 means the object is not present. 1 means the object is present. Now, what is happening here is, let's focus on this first term first. Okay, so this is the predicted value, and this is the ground truth value. Let's consider a case where your object was present, right? And your network also said like it is present. So in this case, this is going to be 1. and this is going to be 1, right? So log 1 becomes 0, and this whole term becomes 0. And your network was actually doing a very good job because the object was present and your network said the object is present. Okay, so we are happy, the loss is 0. Now, if you look at the second term, because the ground truth is 1, this completely becomes 0. So we don't have to compute this. So if your network did the right job, your loss is 0, which means this loss function is actually doing its work, right? Now let's consider the other case when, let's say, the ground truth was 1, but the network said it's not present. Okay, so in that case, what will happen is, let's ignore this first one. Let's go to this. So in this case, this will be 0, that's the predicted value, and log 1 is going to be 0. Again, you can ignore this term because if you just multiply anything with 0, that's going to be 0. Now let's come back to this one. Log 0, you know, is negative infinity, right? And this is 1, so this is going to give you negative infinity, and you have a negative sign outside, which makes this infinity. So which means that if your network is saying, okay, it was not present, but in fact it was present, this kind of loss function or cross entropy is saying, okay, the loss is infinity, which is actually good. And what you do is you compute that loss function for all the samples in your training set, and we just average that. Okay, so that's one kind of loss. You can also compute like mean squared error. This is just you do pointwise comparison. Right? You just subtract the values and you square the values and just take the mean. Okay, so that's another, so that's fine. Again, this is just telling you the difference between these two. So if the difference is like 0, these two will cancel each other, right? But if the difference is high, it will give you like some high value, which means the loss will have some non-negative value. So this is another kind of loss you use. Okay, so let's actually end it here, and we will continue the second part, differentiability, maybe in the next lecture.